Okay, welcome everybody. Welcome back to the second part of our first day of our flat band conference. And now we will have four short seminars. And our first speaker is Vadim Ohanyan, and he will tell us about his recent work on electric field-driven flat bands, the enhanced magnetoelectric and electrocaloric effects in frustrated quantum magnets. Please, Vadim.
Okay, good evening, good afternoon, everybody. I would like to thank organizers for giving me opportunity to present our recent results on aspects of the flat band physics in frustrated quantum magnets. What I'm going to tell you is based on the part of the result presented in this preprint done in collaboration with Johannes Richter, Jörg Schulenburg, and Jürgen Schnack. So as I told you, as I told you, we deal with the magnonic flat band. It's a little bit different concept from the electronic flat band. So I will give a short introduction. We deal with the quantum spin model. Yeah, it's localized magnetic moments on the side of the lattice with the set of exchange interaction parameters Jij, and also in with Zeeman term with magnetic field. For sufficiently large values of magnetic fields, the ground state is fully polarized, and the low-lying translationally invariant excitation above this ground state, it's a magnon. So it's actually the magnon is the translational invariant superposition of flipped spins all around the lattice. Yeah? And it has magnetic moment equal to -1. It has crystal momentum K as a quantum number, and of course it has the dispersion. So the form of the dispersion depends on the lattice structure, and also it could be several branches if magnetic lattice has a few sides in unit cell. And this one-magnon flat band, when one of the branches became dispersionless, just a constant, yeah, can appear only in specific lattice geometries. And in addition to that, usually the certain strict constraint necessary for the set of the exchange interaction parameters. Okay, so the magnon state corresponding to the flat band, of course, are localized within some small region of the lattice of a few sites, which we can call magnon trap. So this is the general conditions for the parameters of the superposition, yes, around this trap and the exchange constant of the Hamiltonian. And actually this concept have been introduced in 2002 in this seminal paper. And of course, very similar concept have been introduced later in the early 90s by Mielke and Tasaki, when they investigate the issue of the ferromagnetic ground state in Hubbard model. But for the purely localized magnetic models, yeah, the concept was introduced in this paper. Yeah. Okay, here are some examples of one-dimensional chain which admit localized magnons, and by both line here, the spin magnon traps are denoted. You can see lattice with the 2-side traps, 3-side traps, even 4 and 6-side traps. And of course, there are plenty of 2-dimensional lattices with localized magnon states, even 3-dimensional. And okay, and now we focus on one particular system, yeah, which called Sawtooth chain, is a corner sharing triangles with 2 type of exchange interaction, J1 and J2, one for the basal line and another one for the zigzag. And as I told you, the flat band, magnonic flat band usually demands strict constraint for the exchange couplings. For the Sawtooth chain, the flat band can appear only when J2 equal to 2 times J1. And this strict constraint makes the experimental experimental observation of the flat band physics an issue. Even if you look into the recent paper when some magnetic measurements have been done for the materials which are well described by the model which is known to have a flat band, no notion of flat band have been observed because we cannot handle the exchange interaction. And okay, here for the spin 1/2 Sawtooth chain with two couplings, the spectrum to one magnon spectrum has the following form. And here are the expressions for the localized magnon states, yeah, which are localized within these free side traps. And under flat band condition, this spectrum became the following. And you can see here the illustration. You can see that the lower branch is totally flat. And moreover, we can easily calculate the saturation magnetic field, which here is equal to 2 times J1. And actually, at the saturation magnetic field, configuration with arbitrary number of localized magnons are degenerate. And thus, even the configuration when we have maximal number of localized spin, when every trap are occupied by a magnon, can be called magnon crystal, is degenerate, yeah, with the saturated state. And that's why if you look at the magnetization curve with the flat band, we will see the jump of magnetization from the magnetization from the magnetization plateau and 1/2 corresponding to the crystal of magnons to the saturation state. And this is a very typical fingerprint of the flat band physics in magnetic systems. Okay, and we found some flexible access to the flat band physics with the aid of the magnetoelectric effect due to Katsura-Nagaosa-Balatsky mechanism. In general, magnetoelectric effect is the interplay between magnetic and dielectric properties in matter, which can manifest in itself as a magnetization dependence on electric field and electric polarization dependence on the magnetic field. So one of the microscopic mechanisms of this phenomena is called after the authors of the seminal paper, Katsura-Nagaosa and Balatsky, K and B mechanism. And the K and B mechanism links the polarization of the bond of the lattice with the double cross product of the unit vector of the bond and spins from the end of the bond. And now our whole Hamiltonian is the following. We have exchange part, Heisenberg part, we have Zeeman part, interaction between magnetic moment and external magnetic field, and we have K and B terms, interaction between electric field and dielectric polarization. I have to mention that recently K and B mechanism became very popular because there are a series of very interesting one-dimensional models with K and B mechanisms which can be solved exactly. And here you can see some recent publication on this topic. And now the system which we have is the Sawtooth chain with two couplings, and as the K and B mechanism concerns the geometry, we have to introduce another parameter, the angle theta between the bonds. And here is the setting of our problem. So we have the chain in the XY plane, and we have in-plane electric field E, which is characterized by the magnitude E and angle phi. And we have magnetic field pointed in Z direction perpendicularly to the XY plane. And we also now we have the system with 6 parameters. And under this setting, the term which described interaction between polarization of the system due to K and B mechanism and electric field has the following form. And now you can see that electric field effectively acts as a Dzyaloshinskii-Moriya spin-spin interaction. of course, when we choose electric field only in plane. Yeah? And thus, formally, we deal with the Sawtooth chain with two exchange coupling, J1 for the basal line and J2 for the zigzags, with three Dzyaloshinskii-Moriya parameters. Each one is proportional to electric field magnitude and depends on two angles, the angle of electric field and physical angle between bonds. Okay, and here you can see again the one-magnon spectrum, but now for the Sawtooth chain with can-be mechanism in electric field. You can see the several phase shifts of sine function, which are linked with the Dzyaloshinskii-Moriya term. It's have quite cumbersome form, and it's quite complicated to make it flat to cancel the k dependence, because we have to satisfy first of all the equality of all phases, etc., etc. But if we use the geometry, the symmetry of the lattice, we can do it quite easily. So as I told you, for the Sawtooth chain without electric field, certain restrictions should be imposed for the exchange coupling to achieve the flat band. And here we found out that if we choose the direction of electric field, yeah, according to the symmetry of the lattice, this means phi equals 0, phi equals theta, or phi equals pi over 2, which means electric field is parallel to the basal line, electric field is parallel to the zigzag, or electric field is perpendicular to the basal line, we can find a series of novel flat bands. And the first one, phi equals 0, is particularly important because in this case, no fine tuning of exchange parameters is necessary. We can drive our system to the flat band, just tuning electric field for almost arbitrary values of the parameters. So here are these conditions. So for arbitrary J1 and J2, we can choose the magnitude of electric field equal to this expression, and we have lower band flat. So this is very important result, as I told you, because it opens new horizons for the experimental observation of the flat bands. And another important point here is that also the value of the saturation magnetic field is lower than for the case without electric field. And here is the
excuse me, 2
yes.
more minutes.
Oh, sorry. And here is the here is the illustration of the previous situation. As I told you, we have the typical fingerprints. It's a plateau and 1/2 and jump to the saturation. And here we have the zero temperature magnetization for the finite system for different value of the J2. We always can tune the magnetic field in such a way to obtain this flat band. And here we can see how flat band affects also magnetoelectric effect. We can have the plots of the polarization dependence of magnetic field and magnetization dependence on electric field, and we can find the same jumps which are connected with the flat bands. And also, as I told you, this flat band are connected with the huge residual entropy. Okay, I will skip this one. And this huge residual entropy connected with the magnon crystal, yeah, can be exploited in certain scheme of the refrigeration using the magnetocaloric effect, or in our case, electrocaloric effect. So here are the plots of the level plots of the entropy, yeah, and you can see this white lines corresponds to the curves of the constant entropy, the isentropy. So you can see that in case if we decrease, for instance, electric field magnitude in isotropic in adiabatic conditions, we can achieve very, very low temperature, and this minima corresponds to the flat band values of the electric fields. Okay, now I came to the summary. The simultaneous application of electric and magnetic fields can dissolve fine-tuning of interaction. And also we obtained interesting reciprocal effect, magnetization jump driven by electric field, jump of electric polarization driven by magnetic field, and enhanced magnetocaloric as well as enhanced electrocaloric effects. So thank you very much.
Thank you, Vadim. Let us thank our speaker. We have time for one quick question. If anyone. Okay, Sergey, please.
Yeah, just a short question. So Vadim, you showed these conditions to derive this flat band.
Yeah.
Am I understanding correctly that this is equivalent to solving a tight binding equation for some single particle problem? I'm entirely meaning the conditions when you derive the flat band.
To some extent, yes, but now we deal with a little bit different Hamiltonian, but of course we can compose such a ground like a localized magnon state, and then we can demand this state to be localized or to be the eigenstate of the Hamiltonian. And this is, to some extent, it's a little bit similar there with the.
No, my question, Vadim, was the following: when you for instance derive these dispersion relations, you gain them from some eigenvalue problem. What I'm saying is that this is essentially a tight binding eigenvalue problem. Is that correct? With some short range.
Actually, not really, because we have interaction here. In tight binding, we don't have interaction.
Yeah, sure, but I mean,
that's
what
the
you
hopping. Here we have hopping terms and as well as some interacting terms.
I mean, there must be a mapping from your spin language to essentially to a tight binding Hamiltonian.
Of course, there is a mapping. That it's not a tight binding because it has hopping term plus interaction, like four particle interaction term.
Yeah, but if you are dealing
each
with
spin Hamiltonian can match to this. Yeah.
Vadim, let's discuss maybe later. Thank you.
Yeah. Okay. Thank you.
Okay. Thank you, Vadim. Please unshare your screen.